Good morning or good afternoon, everyone, depending on where you're joining us from, and welcome to today's webinar. My name is Carl from Business Review, and I will be your host today. It is our pleasure to have Redis Labs with us, who will be presenting this webinar entitled Unleashing the Power of Redis. Today's guest speaker is Peter Caillou, who is Solutions Architect at Redis Labs. I'd like to welcome you to our webinar platform On24. You'll notice that this webinar is browser-based, so if you disconnect for any reason, just click on the link that you received via email to rejoin the session. In order to ask questions, you can send them in via the questions widget, type them into the box at the top left-hand corner of your screen and click submit. We'll allocate some time at the end of the session to address any questions or thoughts you may have. Please use the yellow help widget if you require any assistance, and you can move, resize, and maximize any of the windows in front of you to get a better view of the slides. But for now, please allow me to welcome Peter Caillou.
Thank you, Kyle. So hello, everyone. First of all, Kyle, thank you for hosting us with this webinar. So my name is Peter Caillou. I'm a solutions architect at Redis Labs, and I'll be talking today about unleashing the power of Redis. A bit about myself. So I'm a computer scientist, and my first job was working at TomTom as a software engineer. I was working at the map building backend there. Afterwards, I joined Neo4j and as a consultant, and now I'm a solutions architect at Redis Labs. So my main job or my main task is to make you, as a Redis Enterprise customer, successful with Redis Enterprise. Now about the webinar of today. So we will be talking about unleashing the power of Redis. So this talk or this webinar will actually mainly be based upon the performance related topics of Redis. But I'll kick it off with a brief introduction to Redis for those who are not familiar with Redis. And then we'll talk about some enterprise-grade Redis for example, data grids, how we scale linearly, high availability, durability. This talk will also talk a bit about data grids and actually the cloud nativeness and how we can actually use Redis in a containerized world. But first, let's kick it off, right? For those who don't know Redis is actually fast, and it's actually extremely fast. And what's even more actually is that it's extremely popular. So this is just one of the rankings that I could show you on how popular Redis is. So this is the one from DB Engines. So here we're placed at position 8. What is actually more interesting is that if you look on the database model side, you can see that the first 4 and actually also the 6th one are relational database management systems. So in the NoSQL world, we're actually positioned at place 3. And what's even more, we're actually the first one in the key value store world. There are many other metrics on where you can see how popular actually Redis is. One of those is actually created by Stack Overflow. On a yearly basis, they actually create a survey that includes 100,000 engineers, and it's now the 2nd year in a row that we came out as the most popular and the most loved and the least hated database out there. So what's even more, if you haven't heard about Redis even, it would be that you've been using it already. So lots of big companies are using it already. Some examples here are Twitter, Snapchat, Tinder, GitHub, and Stack Overflow. So to give you some idea on how they're using this, so Twitter is using it for their timeline and following. So every time you go into the app or you go into their website, the results or the feeds of your tweets will actually be served directly from Redis. So only when you tweet, for example, you will hit, or your tweet will be going to a relational database in the backend, but some microservices will take care that your timeline or your personalized timeline is actually populated inside Redis. Snapchat is using it for all their messages they send them across. Tinder is using one of the specific data types of Redis to do geospatial searches for their user profiles. GitHub is using it as a repository router, and Stack Overflow is actually caching their entire website inside Redis. There are many more use cases we can talk about. This is just a brief introduction, but you can find many more actually on our website on redislabs.com. So what is Redis and what are our top differentiators, right? So Redis is an in-memory database, and it's a key value store So those are the kind of like the bit of the positioning of what the database is. And then the top differentiators are its performance, simplicity, and extensibility. So today we'll talk about a lot about about the performance and extensibility. So we'll touch upon those later on. What we won't touch too much upon today is actually the simplicity. So Redis actually has some built-in data types or data structures. So compared, for example, to the simplest or the easiest key value store, which would be, for example, Memcache. The value in Memcache is always a string, while in Redis you will have all different data types, right? So you'll have a string, a set, a sorted set, a hash. So you could see it as memory in a service. All those data types will have some counterpart in your programming language of choice. So you could see it as memory as a service. So this has some benefits, right? Because your set will effectively be served or hosted in memory as a set inside Redis instead of a string. So if you would have, for example, a set, if you would model it in for example, into a JSON document that persists as a string, you would have to, if you would like to do the intersection of two sets, you would have to fetch those strings, deserialize them, those JSON documents, deserialize them, and do the intersection at client side. While with Redis, you can actually ask the database to do the intersection at server side and only transfer the intersection towards your client. But we can talk about that much more, and we will have some webinars in the future about data modeling, but we won't be focusing on this too much on this webinar. So some speed differentiators. So it's entirely written in C. So compared to our key value stores that are, for example, written in Java, this has a huge performance improvement. The data is entirely served from memory, so it's an in-memory first database. We do have durability, so we can persist your database onto disk. We'll talk about that later on. It's a single-threaded, so a single Redis instance will always be single-threaded, and that has some benefits, right? So if, for example, you want to do 5 operations, and you can instruct Redis to do those sequentially, you know that no other client will be interacting during those 5 operations. So most commands are also written into an O1 time complexity. So obviously that's not possible for all operations, for example, on sets, but most of them are actually aimed to be O1. There's access to discrete elements within objects. I already talked about that, for example, when we have 2 sets and we would like to do the intersection of those 2 sets. So that actually also reduces the bandwidth overhead, right? Because you won't have to fetch the entire object to do that intersection. And then also there are some efficient operation differentiators, right? So it's an easy to parse networking protocol. You can actually just telnet to it. And we can also pipeline. So this pipelining, what does it mean? It means that if you would know 20 or 40 or even 5 operations that you want to execute against Redis, up front, you can actually send them in a single request. This is interesting, for example, for batch loading data inside Redis. So a bit about the extensibility. So we've talked about these data types. Each data type comes with a set of commands. But what we did, I think in 2014, we opened up the functionality or the ability to create plugins or modules that you can load inside Redis. And in these modules, you can actually define your own data types and the commands you can execute against those data types. And as a benefit of hosting those inside Redis, you can reuse all Redis simplicity, right? So the performance, the scalability, the high availability, and also the durability. They can be written in C or any C compiled language. And you can also leverage the existing data structures. So you can combine a set of data structures to make a more complex data type. And this actually turns Redis into a multi-model database. With these modules, we can actually host several types of data. Now, the community has been building quite a lot of those modules, and it might be sometimes hard to find your way around in those modules. So we've created a module hub, and in this module hub, we're actually going to certify certain modules. So I'm just showing you now a screenshot of that module hub. So this are just the top 4 listed there. There are a lot more out there, I think around 30, 40 of those modules. But these ones are the ones that we actually think if they got either a certified or an enterprise label or we actually certify them for production use case. And let me just briefly touch upon those 4, right? So the top left one is Redis Search. So if you're familiar with Apache Lucene or Elasticsearch and Solr, which are effectively using Apache Lucene, it's an inverted index. So Redis Search is effectively an inverted index that we can run inside Redis, and it has some benefits, right? Because Redis is written in C, and Redis Search is also written in C, and it's hosting the data entirely from memory. Compare that to, for example, Apache Lucene, which is Java-based and is also disk-based. The worst case scenario we can actually have is that we get up to 5 times performance improvements to any Apache Lucene-based solution. It has been around now for 3 years, and we wouldn't say that we were entirely feature complete, but let's say that the 99% of features that you expect from an inverted index are there. So we can do an autocomplete, we can do full text search, we can do Liebenstein distances, we can do soundex libraries, we can do stemming, we can do aggregations, etc. Redis Graph is another module. Redis Graph is actually going to host your data as a graph, and we're using the Graph Blast library for that. And Graph Blast library is actually going to create your adjacency matrix of all your nodes, is going to persist them into a compressed matrix. And Graph Blast, the library itself, allows you to do matrix operations onto a compressed matrices, and it's very performing. So the API we're building on top of that is actually a Cypher API, which is based on the Open Cypher API, which is originally created by Neo4j, but that we're now actually incorporating too. Then there's ReadJSON. ReadJSON allows you to create a document store out of Redis. So if you have a huge or a large JSON document, you used to have to persist that into the string data type inside Redis. But now with this ReadJSON module, you can actually host that as a tree. And that has the advantage that if you would like to, in a large JSON document, you would like to update one particular part of your JSON document, you can now do that in an atomic operation. Let's say you have a counter somewhere in the JSON document, you can just in a single command instruct to increment or decrement that counter. While in the past you had to fetch the JSON document, deserialize it, update it at client side, and then serialize it and send it back to Redis. And meanwhile, it might have been updated. Redis ML is also an interesting module. We actually use it for machine model serving. So it's not aimed at training your models, but actually to serve them. So once you've trained, for example, your random forest tree, you could send that model towards Redis, and then with a single command, you can actually send your vector to Redis, and we will do the regression or the classification and send you the answer back very fast. Just the key takeaway from these modules is actually that we go into a multi-model database. So allow me to introduce Redis Enterprise. So Redis Enterprise is a product from Redis Labs. So Redis Labs is actually the home of Redis. We're the top contributor to the open source project. And the company actually started off as a database as a service provider. So we started off in 2013. We now have 8,500 enterprise customers on our database as a service platform. And in 2015, we actually took that the software that we're using to host those databases or to serve those databases in the cloud, and we made it available for enterprise customers. And we now have 300 and more enterprise customers that are using this software. So I want to touch briefly upon this because actually cloud providers and database as a service providers, they actually have different incentives, right? So a cloud provider's incentive is actually to sell you as many virtual machines or instances as possible. While a database as a service provider, actually their incentive is to sell you as many databases, obviously, but also to create a higher margin on those databases. So let's assume we talked about Redis before. So if you remember, for example, it was single-threaded and it's in memory. If you would need to find a cloud instance that has, for example, 64 gigabytes of RAM, by default, that would come, for example, with 8 or 16 cores. Now, since it's single-threaded, you can only utilize one of those 16 cores, but you'd still be paying for them, right? So cloud providers' offerings actually they will get a higher margin because you're underutilizing actually those resources. With Redis Enterprise, what we actually try to achieve, because we were a database and service provider first, was that actually we get a higher margin on those resources. So we will do a multi-tenancy in a single cluster, so that actually we can use or reuse multiple cores. We're also going to reduce the actual usage of memory, and we'll see that later on how we do that. And battery, of course, the CPU utilization via the multi-tenancy. So here you can see some overview of the actual features of Redis Enterprise. In this talk, we'll focus more on the left-hand side of those features. So we'll be talking about linear scaling. We'll be talking about high availability with almost instant failover. We'll be talking about how we tackle durability, and also how we do active-active queue distribution. Some other features on the right-hand side, so which already tackled briefly but not too much into depth, is the built-in high-performance search, the multimodalness, flexible deployment options. We'll talk about that briefly too. And then lastly, there's intelligent tiered access. So imagine you have a massive data set. If you would have to host that entirely into RAM, that might become expensive for your infrastructure costs. So what we can actually do is we can offload your cold data onto a flash memory, right? So we will make sure that your hot keys and values are actually living inside memory, while the cold ones go to a flash storage. And that is very interesting, for example, to applications where only 20%, for example, or 30% of your data is accessed regularly, and the cold data is, for example, only accessed on a monthly basis. So how does the architecture look like, or what we do? So you could see Redis Enterprise a bit as a database management system for Redis databases. So typically in Redis Enterprise cluster, we will have 3 nodes or an odd number of nodes. And we will place those Redis instances inside those machines based upon how many resources they have available. So we typically have an uneven number of nodes. The reason why we do that is actually to create, to avoid a split brain, right? So we will avoid a split brain based upon the nodes or on the machines in the cluster, not on the copies or the master-slave replication of our databases. So it's also multi-tenant, so we can in this cluster host multiple databases. So how would it look like? First of all, we could go and create a single database. This database is not highly available, and the master is responsible in this case for all your keys. So if you would like to make this database highly available, we will place a slave counterpart on a different node in the cluster. We'll see later on that we can also do this via rec awareness or also availability zone awareness. Now, if your database tends to grow in either size or in throughput, there's only so much you can do with a single master, right? You're limited to one core. So what we can do is we can cluster your database. So in this example, we're clustering your database into 3 shards, as we call them, and each shard is actually responsible for a distinct set of keys. So now, how do we know which key should reside in which instance? Well, we're actually applying some CRC16 on your key, and then we're doing a modulo operation onto that. So in total, we will actually have 16,384 slots. Now, sometimes you would like to have some data to reside within the same instance or within the same shard. So this is actually some code that is out there. But what we can do is actually we can tag your keys, or you can tag your keys and you can say, well, I would like to have this part of my key to be hashed. So you could, for example, take a user ID, and then all the keys related to this specific user will reside within the same shard. The next thing we can do is actually make this cluster database to be highly available. So once again, as you can see, we will make sure that the slave counterpart of the master shard doesn't reside within the same node or rec zone rec or availability zone. So we have a shared nothing architecture. So you could see it kind of like as a two-layer architecture. So each node will have an open source layer and an enterprise layer. So our open source layer will be what we call Redis Shards or Redis instances. Those are these processes, the single Redis instances that we were talking about in the past. We also have an enterprise layer which consists out of mainly three components. There is a cluster manager. This cluster manager will make sure that in the event that there is a network partitioning, that a master will fail over to, so that a slave will be promoted towards a master in case of a failover. There is also a REST API. Redis Enterprise comes with a user interface, so the creation of all databases or the changes of configuration you would like to make, you can do from this user interface. But it also comes with this user interface is effectively using a REST API, so you can automate everything as you wish with this REST API. It also comes with obviously this it's a management system, so it comes with some LDAP integration to do this management. The third component is this zero latency proxy. Now we'll talk about later on why we call this a zero latency proxy, but because obviously proxy tends to introduce some extra latency. Now this proxy will actually be the abstraction of the database underneath. So from your client-side application, it will look like you have a single endpoint, and you will talk to a single endpoint. And underneath, we might have multiple shards. So your client doesn't need to know if the database is clustered, if it's highly available, if it's durable. That's all abstracted away from your client-side applications via this proxy. This proxy is also great because it introduces us to do some certain things that are not possible with the open source. So for example, we can do TLS or SSL encryption of your data in transit because we will decrypt it then at the proxy side. So if we would place that back again into our three-node cluster, we would get our data path and our cluster management path, right? Each instance will come with some watchdogs. There are node watchdogs. There is a cluster watchdog, so that we can actually enable fast failover. So that was my brief introduction to Redis Enterprise. Let's now talk about how we could see Redis Enterprise as a data grid. So a recent trend, well, it's not really a recent trend, but the trend of microservices architecture and polyglot persistence is real, right? So microservices mean that we will create smaller web services with single responsibility or a subset of responsibilities to counter the big monolith applications. And then polyglot persistence means actually that each single of those web services can actually use the persistence that is convenient for them. So this is great actually because you will use the right tool for the right job, but it also introduces some complexity, as you can see on the screen, right? So we will have, for example, the authentication that will be using a key value store. We could have a session management store with the API, which is using a document store. I'm just picking some of them, right? There's also a customer API we can see at the bottom left that is using a key value store, but also a graph database, for example, to figure out which customers are connected or to make recommendations. There's also a search API, which is specifically using a search or inverted index underneath. So this has some downsides, right? So you will create an increased application complexity. There is also a higher operational burden because there is a higher cost of ownership, right? Each database will come with specialized administrative and scaling and availability requirements. You will also need specific knowledge inside your company to maintain those databases. Lastly, there is also a suboptimal resource usage because each single of those databases will require their own dedicated pods or servers, and that actually reduces your deployment efficiency, as we have seen before. Now, what is great, right? We've talked about Redis Enterprise, which is which is a multi-tenant. So in a single cluster, we can optimize your resources and allocate them to different databases because it's multi-tenant. And we've talked about these modules. So in each single database, we can enable a subset of modules. we can actually simplify this architecture, right? So this is where we see Redis actually as a data grid. So at the bottom we can see that in our Redis Enterprise cluster we'll have separate databases. Some of them have modules loaded. Other ones are the simple plain key value store, right? So now our authentication API is using Redis as a key value store, or has a separate database. The customer's API has a Redis database with a graph module loaded, but is also using some key value store to serve its API needs. The catalog could be doing some caching inside Redis, while the data is actually fetched regularly from the relational database management system. Our search index, our search API is now using a Redis instance with this Redis search module loaded, etc., etc. So this kind of like simplifies your architecture, right? Each database can have a total different configuration. They can scale in a different way, so we'll see that later on how we can scale those databases. They can also have different durability configurations, etc. Now we can even simplify this picture even more, right? So at the top we will see that all these APIs have to talk to each other to keep their databases in sync, but also to serve data to upper lying services or microservices. So one data type we didn't touch upon yet, or two data types actually, is PubSub and streams. So Redis comes with built-in PubSub, which is actually you can publish messages to a certain channel, and then your clients can subscribe to certain channels and receive those messages. Now, the downside of this PubSub is it's fire and forget. So if your client is not listening, we actually you will never receive that messages. That's why there is a second data type which is called streams. It's less lightweight as the PubSub, but it comes with the advantage that you can record all the messages inside a single stream, and then you can either use it as a topic or as a queue. So in a topic, each service can actually go through the entire chain of events and process their messages. When communication drops, they can reconnect and pick up where they left or consume the last message. While in the queue setup, you can actually try to parallelize your work. So in that case, Redis will make sure that each message gets delivered to only one consumer. Linear scalability. So the story I want to tell here is that actually we have on the left-hand side, we have a single master and a slave, and we would like to move over to two masters and two slaves. The reasons why we could do that, I already touched upon them, is either our database grows in memory and it becomes inefficient to serve that from one single process, but also because our throughput requirements increase, and we would like to maintain a very low latency per operation, right? Remember again that a single Redis instance here is single threaded. So how do we do this with Redis Enterprise? I believe you could already see the complexity of doing that. Without Redis Enterprise, you can already see that this might be a burden to do that without any downtime. Now in Redis Enterprise, you have the benefit of this proxy component. So on the left-hand side, all the clients will talk to this proxy. They have an abstraction of this database, and they talk to the single proxy. The proxy always talks to the master. The slave is there to offload the master so that the slave can take up, for example, responsibilities to do durability, to do replication to other clusters. It can also do backupping. It can do alerting, etc. All those functionality can actually be tackled by the slave, so we can actually maintain a very high throughput and low latency on the master. Now, what is the first thing that we do is we add two more slaves to the picture. And those slaves are copies of the first one of the master, the second one of the slave, and they are responsible for 50% of the data set. The next thing that we do is actually we tell the proxy to queue up all the requests for a bit, and we drain all the connections. So we will make sure that everything is in sync. So all the masters and the slaves are all in sync with each other. This takes up a couple of milliseconds. And the next thing we do is we will update the routing table in the proxy with this hashing and algorithm that we discussed before. So now 50% of the keys will be sent to the master 1, the new master 1. The original slave is now M2, and that one will be serving the other 50% of the keys. And the last thing that we do is actually we trim those 2 instances because they actually no longer need to serve 50% of that data. And all this happens, well, the entire process happens depending on how much size you have in your database within a couple of seconds. But your client-side application will not find any downtime, and it will only see a couple of milliseconds extra latency to a subset of operations. So this is really powerful because obviously you don't know initially where your application is going to go and how much scale you will need. But we can actually just keep on doing this process over and over again. And how can we do this? Well, on the left-hand side, we have a single node with 4 shards. We can add another machine to the cluster. At that moment in time, it won't be hosting any shards. And then we can rebalance your shards. So then we will have 2 per machine. And then we can do resharding again. And we can do this over and over again, right? We can add then again another machine to the cluster and scale it out again. So I mentioned this zero latency proxy. Why do we call this a zero latency proxy? So that's because actually we do multiplexing and pipelining. So our proxy will maintain a fixed number of persistent connections towards these shards. And when your application on the left-hand side sends 7 different requests simultaneously, we will actually send those requests over those persistent connections. So you can see that requests 1, 2, and 3, and 4 will go over the first connection, and 5, 6, and 7 go over the second connection. So that is effectively multiplexing. Now, the second thing we do is we will pipeline them. So I've talked about it previously. So we can actually send multiple operations in a single request to the database. And those 2 things combined makes that, well, in the worst case scenario, there will be a zero latency impacts, and in the best worst case scenario, we will actually improve the throughput and the latency towards your application. So something about displacement, there are different scenarios, but for each database you can have a separate configuration. So on the left-hand side, we will have a dense placement policy, which means that we will place as many master shards on the same node, and there's only a single proxy endpoint enabled on that node. We can also do a sparse placement policy. Why would we do that? Well, because on the left-hand side, we're limited to the bandwidth of a single node, or the network bandwidth. While on the right-hand side, we can actually better utilize the network bandwidth of those 3 machines. Now, what happens if you hit, for example, on the right-hand side on the first proxy, and your key doesn't live within that node, you will have to go over the wire to the other machines, or the proxy will go and forward that request. So you will have some more inter-nodes traffic, yet you can actually increase your network usage or your throughput of your database. Now, you can see that this won't scale linearly. So the next step what we can actually do is we can create or use a client that is a bit more smart, and instead of the hashing actually happening, the hashing of the key and figuring out at which slot it resides, we can actually do that at client side. But each client will actually make a number of connections to different proxy endpoints. However, the client will know which key resides onto which node in the cluster. And in that way, we can actually fully utilize the bandwidth of each node in the cluster. And we've tested that, quite thoroughly. So the first thing you can see is that here we create actually a 6-node cluster. I know we need an odd number, but forget about that. A 6-node cluster with 120 shards. And we get in the screenshot, we get up to 11 million operations. And I want to add that all those operations are sub-millisecond latency, and that in this specific benchmark, we took a reasonable pipelining, so which means that each request will contain 9 operations. But to prove actually the linear scalability is that if you would go from 6 nodes and 120 shards, we go to 12 nodes and 240 shards, we get 20 million operations per second, still sub 1 millisecond latency. And then again, obviously, if you go to 18 nodes, we add another 6 nodes, and on 120 shards, we get 30 million operations. And in our latest benchmark, you can actually go into the link above later on. We actually have 50 million operations with 26 nodes, sub-millisecond latency. Let's talk about high availability. So we have some lessons learned We've been running Redis Enterprise for 5 years in production. We're managing, we've managed 550,000 databases, over more than 50 data centers or availability zones. We had 2,000 node failures and 0 data loss. And we had a complete data center outages even. So we did learn our lesson, and our enterprise software has been being improved continuously. So I will talk about some concepts that we do for high availability. The first one is that we quorum on the number of nodes and not by shards. So a typical setup that you would expect is that a master will have 2 slaves to be highly available. Now we've separated the responsibilities, and we will actually make sure that we'll have a quorum based upon the node level and not on a database level. So that has some benefits with regards to your infrastructure costs, right? So we will have a single master and a single slave. Because in a 3-node cluster, by the way, according to computer science, you can only survive n failures in a 2n+1 cluster. So in this cluster, we can only survive 1 node outage. So there is no point to even have a third copy of your database. A third node should only be there to create a majority or to figure out which other node is the majority in your cluster and to avoid a split brain. So if you could imagine, for example, that we would have a 2 terabytes database, in the left-hand side, we would have 2 terabytes of RAM, 2 terabytes of RAM, 2 terabytes of RAM in those 3 machines, while on the right-hand side, we actually can have a very small node that doesn't have that much memory, that is just there to establish quorum. And this is one of the things that I talked earlier on, where we have different incentives than, for example, cloud providers. So it's not only the reduced cost of memory, it's also less network traffic, and also because if you have a multi-tenant cluster, you can actually host more databases within the same in a smaller infrastructure. So it's easier to manage. Small clusters tend to be easier to manage. The second concept is that we can do pure in-memory replication. So the copy from a master to a slave would go in the basic open source would go by taking a snapshot of your database, serializing to disk, copying this a snapshot, and then loading it inside memory. You can also do some open source diskless replication, where you will actually avoid the first snapshot, and you would snapshot directly to the second machine. Now we've updated Redis to actually do pure in-memory replication, so which is up to 2 times faster, and it's actually only limited to the network bandwidth in between those machines. So we're no longer doing this snapshotting. We also made the Watchdogs part of the cluster. So on the left-hand side here, we can actually see that the Watchdogs, it's just a possible setup, right? The open source Sentinels would be not part of the cluster. So what happens on the left-hand side is that there's a network partitioning, but the Watchdogs can still see the master, so they think everything is fine, while your clients can no longer access your database because they can only talk to the slaves. We made the Watchdogs part of the cluster. We also have 1 slave less, as you can see on the right-hand side. So what happens is that in the case there is a network partitioning, the Watchdogs on the right-hand side will see that the master is no more reachable, and they will trigger a failover instantly. So in this way, we can actually trigger a failover much faster. Obviously, it depends upon which deployment you have and what the stability is of your network infrastructure, but typically we get up to less than 10 seconds or single digits failover time from master to slave. Then the rec zone awareness, or the multi-availability zone awareness. So we can actually make sure that your slaves and master and slaves are never served within the same availability zone or the same rec. So this has some benefits that if an entire availability zone or your rec goes down, your database all your databases will still be available. So one requirement that it has is that the sum of the 2 other availability zones, the nodes in the cluster should still be more, or the sum should be more than the 3rd availability zone. So in the event that one availability zone goes down, your nodes still form a majority or a quorum. Let's move on to durability. So one of the things that we saw is that for data persistence, actually, for both persistent and ephemeral storage, typically that is placed together with the nodes on the same machine. So in the event of the machine entirely failing, you would have to spin up a new instance. So one of the things that we did is we actually split up our ephemeral storage and our persistent storage. So our persistent storage will be mounted to a network drive, for example, and everything will go into that persistent storage. So in the event that we need to create a new instance, we can actually reattach that volume, and it will be populated with the latest state that we have available. This is particularly interesting, for example, for when we move on to pods, right? So each node could be, for example, a pod. And if you're familiar with Kubernetes, we'll touch upon that briefly in a bit. We can actually we can use a stateful set and attach a persistent volume back to this pod, and everything will be healed perfectly as before. A second concept is actually we have tunable durability. So we have different configurations for persistence. So we could have a single non-replicated instance, and we could serialize your data to disk. Do your data to disk. By the way, we have three options here. We actually have multiple options, but the three main options is that we can do a snapshot, which would be taken, for example, on a regular basis. But if you want to keep the latest state of your database persisted, there are two options. There is either an append-only file on every second and on every write. So if you would do, for example, the append-only file on every write on the left-hand side, that would introduce an extra latency, obviously, for your write operations. So we could tune for speed. So that's the middle of operation. So your slave will be tackling this persistence. So which means that your master actually, without any impact of the whether there is persistence or not, would still have served the same throughput and latency. And we can also tune it for reliability, and then both the master and the slave will actually take this persistence task. Two more chapters to go. So this one is talking about cloud native. So I'm assuming that lots of you are going to the cloud or are already in the cloud. There are also different cloud vendors out there. So we could imagine in the future an application where we have some Redis Enterprise cluster in Azure, in AWS and Google Cloud, and also on-prem for more secure private data. So what we see that other applications actually go for either an eventual consistent system or a strong consistent system. Now I know this 100 milliseconds is just a quite arbitrary number. From the 100 milliseconds to the 200 milliseconds does make sense in those systems. So does that make sense inside Redis, right? So Redis is an in-memory database. You're already paying something extra to serve your data entirely from memory. So does it make sense to wait till your data has been converted and replicated to the other data centers? So we wanted something more smart. We wanted to have local read and write latencies. And so for that, we used a concept which is called CRDT, or conflict-free replicated data types. It's not something that we invented. It has been around, and it's based upon academic research for quite a while. It's a consensus-free protocol, and it's effectively strong eventual consistency. So it's going to detect conflicts in write operations based upon vector clocks. So we will use those vector clocks to make sure that there's a causal ordering of events. And if there is a conflict, each data type, so we've talked about these different data types, will have a specific conversion function or resolution function. So this is how it could look like. We have a geo-distributed database in 3 locations, and the strong eventual consistency actually gives us 1 millisecond latency. An example of this conversion function could be we have a counter that resides into 3 replicas. We would increment the counter at the same moment in time, so in the same causal ordering of events. So what is the conversion function going to be? It's quite easy. It's just a sum of the operations. So plus 200 minus 300 plus 1,000 is plus 900. So we go from 500 to 1,400. So all replicas will see eventually strong eventual, actually the 1,400. A different conversion function is, for example, for sets. If you would add B, add A, remove A, then actually the addition is going to win over the removal. So every replica will effectively still see the element A in its set. I'm speeding up a bit to leave some time for Q&A. So the last section is actually containerized. So what we kind of wanted to do is make our Redis Enterprise offering available onto multiple platforms. I'm just picking one here, which is Kubernetes, which tends to be very popular nowadays. So Kubernetes, for those who are not familiar, it's a portable, extensible open source framework platform for managing containerized workloads and services. So it used to be only for stateless workloads, but since 1.8, there has been support for stateful. By the way, we're at 1.11, I think, for Kubernetes. So that has matured. Meanwhile, it encourages the usage of microservices, so it fits entirely into this polyglot persistence and microservices world, and it should also be portable. So it should enable you to have less cloud lock-in because you could move your entire Kubernetes cluster to a different provider. The only thing I want to touch upon this is actually that Kubernetes is going to orchestrate, but it doesn't really actually orchestrate your containers. It's going to orchestrate the resources and deliver them to the containerized applications based upon how you declared or described how many resources you should have available for each container. It also does much more, right? So it also allows you to do some basic health checks, but also is going to do self-healing. In the event that a pod dies, it will make sure that a new pod is spun up. When it spins up a new pod, actually in a stateful set, it's going to reattach that persistent volume to that pod. And so we talked about durability previously. So we're actually using the stateful set capabilities of Kubernetes. Now we've also created a Helm chart. So Helm is kind of like the dependency manager, or like, well, the package manager for Kubernetes. So you can actually consume some pre-configured Kubernetes resources. With a single instruction, you could deploy a Redis Enterprise cluster. I've talked about that more in a different webinar. I will share the link to that one later on, but I just wanted to briefly show you how that would look like. So here in this example, we could see that we have 3 pods with a red square on top of them. Those are actually going to be our nodes of our cluster. And you also see that they will have a volume attached to those. So these pods are part of our stateful set. And we also have a controller. This controller will actually make sure that all databases that are running within your cluster or Redis Enterprise cluster are actually served as a headless service within Kubernetes. And how does this look like if you would take a clean install, for example, and we would do this, for example, on PKS, the Pivotal Container Service. We could see that the second section, screenshot, has, for example, 3 Redis spec nodes, 0, 1, and 2. And the third section, actually, you can see that that's actually the output of the stateful sets. We could see that there's a desired state of 3, and there's currently a number of 3 available. The last one is actually going to be the controller. The controller is the pod that is going to make sure that your database is exposed as a headless service. And we could see that actually on the first section where we have Redis spec and Redis spec headless, which is the name of the database that we're exposing. This is how it could look like in OpenShift. So it's a similar setup. Well, one more thing I want to touch upon the stateful set is that actually it allows us to do rolling upgrades. One thing that is a contract of stateful sets is that only one pod at a time will be touched upon. So Kubernetes will make sure that is the case. So, and because we have in case we have a high available database, we can actually bring one pod entirely down and replace it with a different pod, right? So we could either make sure that the pod has more resources, or we could make sure that, for example, it has a new software or the newest software of Redis Enterprise installed without any downtime. So just a recap about this webinar, I spoke briefly about Redis, about the 3 top differentiators being performance, simplicity, and extensibility. We talked a bit about multi-model databases and data grids. We talked about how we could actually scale Redis linearly, and we can actually do that without any downtime. We also spoke about how we tackled or which concepts we enable within Redis Enterprise for high availability and durability. And lastly, I talked briefly about how we can actually, with Redis Enterprise, support cloud-native data and even run Redis Enterprise within a containerized application. So I still have some resources for you. So these are the resources. So the first one is where you can actually find the Helm chart to deploy into your own Kubernetes cluster, that will go with just a single command. It has quite some good documentation on that GitHub repo. There's a Redis Enterprise Docker image you could use to play around on your local machine. The webinar I've spoken about, I will actually give a demo of this Redis Enterprise on Kubernetes is linked there. We also have a new Kubernetes operator to work together with OpenShift, which has actually more insights about, or has more is more clever about which operations you can do within Redis Enterprise cluster. There's our module hub I talked about, and if in case you still have any questions after the Q&A, you can always email expert@redislabs.com. So thank you so far for listening to me. Once again, my name is Peter Caillot. You can email me always on peter@redislabs.com, and you can find me on Twitter @Caillot. So and now I hand it over back to Carl for the Q&A.
Hello, Peter.
Yes.
Should we carry on with the Q&A session?
Yes, please.
Good, good. So we received some very good questions here, actually. I'll start off by reading the first one. So the question reads, how does your cloud offering compare to Elasticcache?
Okay, so Elasticache. So great question, right? AWS also has some Redis offering for managed services or for managed Redis enterprise, Redis databases. So I touched upon already on a couple of them, right, in my slides. But a couple of things that we have as a benefit is that we will always have the most recent version of Redis available. I believe that, for example, Elasticache is at 3 something, while we're actually going into Redis version 5 inside Redis Enterprise, and also for managed applications. So we also have a better usage, or we'll be consuming your resources in a better way. So that will actually reduce your total cost of ownership. It will be actually less expensive to use Redis Enterprise from Redis Labs, either in the cloud or on-premise, than using Elasticache. And then the last benefit that we have is that all the modules are actually licensed differently. So if you would like to use those or consume those modules, you can't use them in Elasticache. You will have to go via Redis Labs.
Thank you for your detailed answer there. We've got another interesting question here. It reads, how easy is it to install Redis Enterprise?
So I've talked about installing Redis Enterprise on Kubernetes, but obviously you can also do that on-prem in your own local data center. So it's quite straightforward. So we support both Red Hat 6 and 7 and Ubuntu Xenile and Trusty to install Redis Enterprise. So it does come with some configuration options. And but I have to say that we have been automating this quite extensively. So we do have, for example, Ansible and Chef and Puppet scripts available. So you can actually, when you go to, for example, to the Ansible Galaxy, you could find this Ansible script and deploy just as convenient as with the Helm charts. You could deploy Redis Enterprise onto your local data center. That said, you can also still use our Docker image, which is also very straightforward to use in your local environment, for example.
Thank you
so
very much.
Fairly easy.
Thank you. Just a reminder to everyone as well, you can still submit your questions using the Q&A widget, which is located in the top left-hand corner of your screen, and then clicking submit. The next question that we have here is, do you have any offering on PCF?
So good question. So I've shown how we can, for example, use our Redis Enterprise setup to deploy to Kubernetes, and I've even shown the screenshot on how this is deployed into PKS. But we also have an offering that is actually ready for Pivotal Cloud Foundry or actually Cloud Foundry. So yes, we do have that, and we do have support then for the broker that, for example, that would run inside PCF and that is deployed via the Pivotal Cloud Foundry's Bosch setup. We're actually going to be present at the Cloud Foundry EU Summit. So if you want to hear more about that, I can definitely forward you to that.
Thank you very much, Peter. An interesting question here. It reads, how do you see Redis differ from Oracle Coherence regarding how you use it or expect to use it?
Good question, right? So Oracle delivers Oracle Coherence kind of like as a caching solution with their licenses. However, it's very complex to set up, and I'm sure that people that are familiar with setting it up are know that it's quite complex. It involves quite a lot of machines that you would have to do, and then that's one thing, right? So our setup will be simplified. So it will be less overhead to deploy, and also it will be we have a less steep learning curve for consuming Redis. It's very straightforward. It's very easy and convenient.
Thank you very much for your answer there. Thank you all as well for submitting your questions. Remember, you can still submit your questions using the Q&A widget, which is located on the top left-hand corner of your screen. Got another question here. It reads, how does Redis Search compare to Lucene-based solutions?
So that's a good question. So I've tackled upon it briefly. So Apache Lucene is it's longer around, obviously, right? So it's an inverted index that has been around for quite a while. But one of the downsides is that it has, first of all, it has limited memory capabilities itself. So the address space is not that big of a single partition. Then it's also disk-based, and it's written in Java. So those three things combined makes when we would compare a single Lucene instance to a single Redis instance with the module deployed. If you would compare them, that we get up to 10, 15 times performance improvement. Now that's obviously a bit of a lab test, so that's only in specific scenarios. But even in the worst case, we get up to 5 times performance improvement. So I see Redis Search being used into applications that are that require very low latency, a very snappy response time. So, for example, if you have a search catalog on your website where you would like to find products very quick, I believe that Redis Search is the better solution. While, for example, Lucene-based solutions are more geared at, for example, large data sets where you have, for example, you have less of a need of a low latency response. For example, the Elk stack, which is based for logging messages of your clusters, it doesn't require a fast response time, and it does require to go through a lot of data, and it doesn't need to be so instantaneously available, right? So it's better to not put all your log files into memory. It's going to cost you much more money. However, you do get with Redis Search, you do get obviously the online transactional use cases that would go much better or much faster. Sorry.
Great, thank you for your detailed answer there, Peter, and thank you all for your questions. But unfortunately, we have run out of time for any more questions. So that just leaves me to thank Peter for what was a great presentation, and thanks to Redis Labs as well for sponsoring this session. To the attendees, you'll receive an email tomorrow telling you how you can access the on-demand version of this webinar. You can access this through our website, which is www.business-review-webinars.com. Please continue to ask questions and interact with the widgets as the on-demand version remains interactive. We look forward to sharing further webinars with you, so please keep an eye out on our website and follow us on Twitter at BRWebinars for daily updates, and also join our LinkedIn group, Business Review Webinars. Thank you once again for tuning in, and I all hope you have a great day. Thank you.